Hi everyone. So in this video, we're going to be talking about a property that certain types of functions have called being one-to-one. And we'll see that functions that have this property also have something that is called an inverse function. So inverse functions are, it's a pretty important topic. So we'll be spending a few videos talking about inverse functions. And so this video is going to just be a basic introduction, and we'll delve more into the details of exactly how inverse functions work in the next couple of videos. Okay, so I wanted to start with a warm-up, and this goes back to something we talked about in the first week of the quarter. So I have three tables written here, and I want you to figure out which ones of these tables are functions and which one is not a function. And then the ones that are functions, I want you to think about how would you describe the difference between them, because there's some kind of property that one of them has that the other one doesn't. So again, you're figuring out which of these three are functions, and then of the ones that are functions, how would you kind of describe the difference between them? Is there one thing that's true about one of them and not true about the other one? So pause the video for a moment, think about that, and then come back. Okay, so which one of these is not a function? Well, we talked about in the first week of class when we were learning about the definition of a function, that a function can only have one output for every input. And so that disqualifies this third table. This is not a function. And so why is it not a function? Well, it comes down to this part, right? So the issue is that we have the same input and we have two different outputs going with that input. So we have the same input, and that same input is being sent to two different outputs. And so the issue is, if you were trying to evaluate f of, or I guess this function, we're calling it h. Well, it's not a function, but this table, we're calling it h of x. If you tried to evaluate h of 2, it would be unclear what your answer is. So that one is not a function. So both of these other two are functions. And so they're functions because there's no ambiguity when you plug a number in, right? You can plug in for let's start with the one on the left. You can do f of 1, f of 2, f of 3. They all give you a clear answer. For the second one, again, you can do g of 1, g of 2, g of 3. They all give you a clear answer. The issue with the third one was that we couldn't figure out which one was actually h of 2. So these first two, they're both functions, but there is something a little different. I'd say one of them is in some ways maybe a little clearer than the other. So which one of these two functions seems like it has a little bit more kind of clarity and straightforwardness? You might say the first one. So what do I mean by that? Well, notice that in the first function, every input goes to its own individual output. Whereas in the second function, it's still a function, but notice that two inputs have the same output. And so there's nothing like wrong with that per se, but it means that the function does not have this special property, which is called being one-to-one. So this function here, the first one, this is one-to-one. So one-to-one basically means that every input goes to its own individual output. One input, one output. So the second one here, this one is not one-to-one. So why is this not one-to-one? Well, basically because we have this situation here where we have two different inputs and those two different inputs are being sent to the same output. So I know it can get a little confusing, what's the difference between the rule for a function versus a rule for one-to-one? Just think about it again. A function basically means that you're able to plug one number in and have a clear answer. Whereas being one-to-one is more about the outputs. It's saying, if you compare all the different outputs, do you have repeated outputs? Are there different inputs that are going to that same output? Okay, so I'm going to define kind of more concretely what it means for a function to be one-to-one, and then we'll look at a couple of examples of functions and talk about how you can figure out in general whether a function is one-to-one or not. So a function is called one-to-one if no two inputs have the same output. So another way of saying that would be that every input has its own individual output. There are no repeated outputs. So I want to think of some examples of functions, and I think generally it's easier to come up with examples that are not one-to-one. So I want to start with brainstorming some examples that are not one-to-one, and we'll look at the graph of one of them and start to see what the graphs look like. And then once we have that, then we'll talk about examples that are one-to-one. So what are some examples of functions that are not one-to-one? So try to think of an example. Maybe pause the video for a moment and think of what are some functions we've seen so far in this class that do not satisfy this one-to-one property. So personally, the first example that I tend to think of would be f of x is equal to x squared, right? So that is not one-to-one. And how would you kind of demonstrate that it's not to one, or that it's not one-to-one? Well, if you plug in, for example, let's say -2 and +2, you get the same result, right? F of -2 is 4, f of +2 is also 4, so you have repeated outputs. Another example of a function that is not one-to-one would be absolute value of x. So again, if you plug in, let's do -2 and +2, you get the same result. So one thing I just want to point out, and I'll give you an example next that kind of goes against this, both of these functions that I just put here, these are both what we called even functions, right? So they have the special even property. So for these two, specifically, if you plug in the negative and positive of the same number, you're getting the same result. That does not need to be true in order to discount the function from being one-to-one. So these two examples, which are probably like the first ones that would come to your mind, these ones, I guess, are like the way that they're not one-to-one is a little bit more specific, right? They're not one-to-one because specifically when you plug in negative and positive versions of the same number, you get the same result. But just to give you another example that doesn't quite fit that mold, but that is still not one-to-one. So the function h of x is equal to x minus 1 squared is not one-to-one. So I'll sketch the graph of it in a moment so we can kind of make a connection between the graph and what's going on with this one-to-one property. But let's come up with an example. So for example, I'm going to plug in the number 0 into this function and see what we get. So if we plug 0 into this function, we get 0 minus 1 squared, so that's -1 squared, and that's 1. So what would be an example of another number that we could plug into this function where we would still get 1 as the output? Can you think of a different x value that we can plug in and still get that same output of 1? Well, we could plug in 2, right? If you plug in 2, you get 2 minus 1 squared, which is +1 squared, which is also equal to 1. So in this case, this is actually not an even function. It's not a function where plugging in the positive and negative of the same number gives you the same result, but it is still not one-to-one. So it doesn't matter what the two numbers are that you're plugging in. All that matters is that you're getting the same output from both of them. If you get the same output from two different inputs, regardless of what those inputs are, that is considered to be not one-to-one. So maybe let me just change the color of this to separate it out a little bit better. So what does the graph of this function look like? Well, we learned from transformations that it's going to be a parabola that's been shifted to the right by 1. So I'm just going to sketch the graph of this real quick. Okay, so it looks something like this. So how can we kind of visualize this idea of not being one-to-one? Well, we have these two different points, right? We said that h of 0 is equal to 1. So let's kind of point out where that point is. So h of 0 equaling 1, that would be referring to this point here, right? This would be the point 0, 1. And then this point over here, this is the point 2, 1. And so what we can see is that basically we have two different x values that have the same y value. And that's really the same as, that agrees with our definition of one-to-one, right? One-to-one is basically saying if you have two different inputs and those two different inputs give you the same output, then it's not one-to-one. And the way that that plays out in the graph is that we have two different x values that have the same y value. So we have two different x values with the same y value. And so in a little bit, we'll see that there's a test that you can do to a graph that will really pinpoint this idea of whether you have two different x values with the same y value. Okay, so what's an example of a function that is one-to-one, or some different functions that are one-to-one? Well, I think it will be easier to come up with examples once we know this test that I'll tell you about in a minute. But let me just tell you a couple of examples and we'll kind of see why they are one-to-one. So f of x is equal to x cubed is one-to-one. And basically, the way you can think about this function being one-to-one is every different number you plug in is always going to give you a different result, right? Like, why was it that we were getting repeated results with these functions that are not one-to-one? Well, it's because when you square a function, it doesn't matter whether your input, or when you square a number, it doesn't matter whether that number was negative or positive, you get the same result. So there's basically a way with squaring to get the same result from different inputs. Whereas with cubing, it just doesn't have that same property. You can plug in, every different number you plug in is going to give you a different result. Another example of a function that is one-to-one would be a linear function. So for example, we could say 2x plus 1 is one-to-one. And so what does that graph look like? Well, it's a line with a slope of 2 and a y-intercept of 1. So that looks like this. And so what we can see is that we're just not getting that same kind of repetition of y values, right? So let me just color code this. I meant to do that. So up here, what we saw with the function x minus 1 squared is that we had different x values that corresponded to the same y value. And we're just not seeing that happen here, right? Every time you go to a different x value, the function is moving on to a different y value. It's not like bending back in order to repeat certain y values. So this function is one-to-one. So every input has a different, I'll say it that way, output. Okay, so what is the kind of test that we can do to graphs to determine whether a function is one-to-one? Well, remember that we had something called the vertical line test for functions, for determining whether something's a function. So now we're going to have something called the horizontal line test that is for determining whether functions are one-to-one. So I'll define the horizontal line test in a moment, but let me just kind of show you on these examples. So notice that on this example, if I draw a horizontal line, it crosses the graph more than once. And so why does that correspond to not being one-to-one? Well, because we can see that we're at one specific y value, right? I drew this horizontal line at a y value of 1, and we hit the graph at two different x values. Whereas this function, I can draw a horizontal line wherever I want, and it's only ever going to cross the graph once. So one-to-one only crosses the graph once, not one-to-one, it crosses the graph twice. So let's write that down a little bit more officially. So this is what's called the horizontal line test. So the horizontal line test says that if you can draw a horizontal line that crosses the graph of a function more than once, that would mean that it is not the graph, or sorry, it is not one-to-one. So I'm just going to sketch a quick example here. So let's say that we had a function that looked like this. So this function would not be one-to-one, right? Because if I were to draw a horizontal line, basically almost anywhere on the graph, the only place I could draw it that would only cross the graph once would be like up here. But there's plenty of places you can draw a line and that it would hit the graph twice. And so basically what's going on here is that we have a single y value, right? The horizontal line is at a specific height, and we have two different x values that go to that same y value. So this would be an example of a function that is not one-to-one. So what does it look like if it is one-to-one? Well, we saw an example a moment ago. I'll sketch kind of a different example. So if we had a function that maybe looked like this, so this function is one-to-one because anywhere where you draw this horizontal line, it's only going to cross the graph once. So this one is one-to-one. Okay, I just want to remind you of what the vertical line test is, because I think a lot of students tend to get mixed up between the two. And I really want you to go back to I really want you to understand why the horizontal line test is the right thing for determining whether something is one-to-one, and why the vertical line test is the right thing for determining whether something's a function, rather than just trying to memorize, oh, there's some kind of line test. So again, just to say it one more time, the reason that the horizontal line test is the right thing here is because by drawing a horizontal line, you're picking one specific y value, right? So this height is one y value. The height where you're drawing the line is one y value, but what are you getting down here? You're getting two different x values. So you have two inputs with the same output. Now, what was the vertical line test? So I'll say, don't confuse this with the vertical line test. So the vertical line test is just for determining whether something is a function. Okay, so let's see how the vertical line test works and just kind of, again, try to understand what that has to do with the definition of a function. So the vertical line test, so I'm just going to sketch an example of a graph here that we'll see is not a function. So something like this. So this would fail the vertical line test. So if we were to draw a vertical line through the graph, we would see that it would cross the graph more than once. So that would tell us that this is not a function. And so why does that kind of fit with the definition of a function? So when you're drawing a vertical line, that means that you're looking at one specific x value, right? You're by drawing a vertical line at an x value, you're focusing in on the x value. But then when you have these 2 points, these are two different y values. And so that would tell you that you would have one input that goes with two different outputs, while versus this one was saying that you have two different inputs with one output. And just to show you real quick, like if I took something that looked just like the function that we drew that was not one-to-one, it still passes the vertical line test, right? So the vertical line test cannot tell you whether something is one-to-one or not, right? This passes the vertical line test. There's nowhere you can draw a vertical line that will cross the graph more than once, and that's because this is a function. However, we can't tell from the vertical line test whether something is one-to-one or not. That's where we have to use the horizontal line test. Okay, so now we're going to move on to talking about something called inverse functions. So if you have a function f of x, and that function is a one-to-one function, and by the way, we'll see why I'm adding in this extra part about if you're starting with a one-to-one function. Just bear with me while I write down the definition of an inverse function. We'll come back to this idea of being one-to-one. So if f of x is a one-to-one function, then there is another function and the way that you denote that function is f with this little -1 exponent of x. And so this function is called the inverse function of f of x. And sorry, I just realized I have to scooch this down a little bit. And so what is this inverse function? Well, this inverse function is defined by the following. So the way that inverse function works is that f inverse of a number b is equal to a number a if f, the original function of the number a, is equal to b. So this might seem a little bit confusing at first. I think once we get into examples, it'll become a lot clearer what's going on. But let me just kind of reiterate again what's going on here. So we're starting with a function, right? We're starting with a function f of x that is one-to-one. And so if you start with a one-to-one function, then there's this other special function out there. And this other special function is called the inverse function of f of x. And so basically the way that this inverse function works is that it kind of goes backwards of f of x. So if focusing on this part, so if you plug a specific number into your original function and you get some certain output, well, the inverse function is going to reverse that. So if you plug the output of the original function into the inverse function, you get the corresponding input. So it kind of just goes backwards. So let's look at an example, and this is just actually, oops, and I need to scooch this down now. This is actually the same example that we looked at the beginning of this video. So this is remember we had three different tables, and this was the one that ended up being both a function and specifically a one-to-one function. So here's our function f of x. So we know that f of 1 is equal to -2. We know that f of 2 is equal to 5. And we know that f of 3 is equal to 4. So how would the inverse function go? Well, that would mean that f inverse of -2 would be equal to 1. F inverse of 5 would be equal to 2. And f inverse of 4 would be equal to 3. So does that kind of make sense? It's basically just asking you to work backwards. It's this function that kind of reverses the roles of inputs and outputs. That's really the main way I like to think about inverse functions, is that it switches the roles of what are your inputs and what are your outputs. So the numbers that were originally the outputs, right? These are the outputs of your original function. Those become actually the inputs of the inverse function. And then the numbers that were originally the inputs of your original function, well, those become the outputs of the inverse function. So inputs and outputs are switching places. And so let's say we wanted to actually make a table for our inverse function. What would that table look like? Well, now the numbers that were originally on the output side from the original function, well, those are now on the input side. And then the outputs are on, or the original inputs are now on the output side. So if we compare the table that we originally had with this new table that we just came up with, all that really happened is that the input and the output columns swapped. So at the end of the day, that's really how inverse functions work. So why is it important that the original function is one-to-one? Well, let me show you what would happen if we tried to use a function that was not one-to-one. So why does your original function f of x need to be one-to-one? Well, let's see what would happen if we tried to do the same thing we did above with this function. So this is from the beginning of the video. This is one that, again, it's a function, but it's just not one-to-one. So based on this function, we know that g of 1 is equal to 5, g of 2 is equal to 5, and g of 3 is equal to 4. So the problem would be if we tried to do g inverse of 5, we wouldn't know which one to say, right? Would our answer be 1 or 2? And so what we learned from the beginning of the quarter is that when you have a function, and remember this inverse thing, it's a function. It's itself a function. It kind of comes from an original function, but it becomes its own function as well. And so in order for this inverse to be a function, when you plug in one number, you can only get one answer, right? It needs to be well defined. It needs to be very clear what your answer is. And so if you do g inverse of 5, well, it's not clear what your answer is, right? There's two different answers it could be. And so this basically tells us that there is no inverse function. So g inverse of x basically would not be a function. And why is it not a function? Well, it was because our original function, g of x, is not one-to-one. So one other thing I want to say is something about the notation. So I just want to make kind of a note about notation here, and I'll put this little warning symbol because this is kind of a common misconception. So f inverse of x does not mean that you are raising f of x to the -1 power, right? Like, so for example, if you, let's say you had, I don't know, 4 to the -1. So if you remember your exponent rules, another way of writing 4 to the -1 would be 1 over 4. So that's true. What I just wrote down here is true. If you take a number and raise it to the -1, that means that you're doing 1 over whatever that number is. But that's not what's going on here. So you don't want to think of this as an exponent. That's really kind of the important thing here, is that this is not an exponent. I mean, it's an exponent in the sense that it is kind of above the function, but it's not an exponent in the sense that it means you're raising it to a power. You want to just think of it as like a symbol. It's a symbol that means inverse. So maybe I'll write that down here. It's just a symbol that means inverse. And by the way, the way you would read this out loud is you would just say f inverse of x. You wouldn't say f to the -1 of x. You would just say f inverse of x. And maybe I'll even make a note of that up here. So when we write f inverse, or when we write something like this, the way you would pronounce this out loud is you would say f inverse of x. So I want to do another example of basically coming up with the inverse function for a particular function. So let's look at the original function we're going to be looking at is going to be f of x is equal to x cubed. So how do we know that this function has an inverse? Well, it's 1-to-1. We already mentioned that, but let's actually sketch the graph of it so that we can really see the fact that it is 1-to-1. So remember, the function of x cubed is going to look something like this. And so we can see it has this shape where it doesn't double back, right? It doesn't end up having any repeated y values. It just kind of keeps going and going. And so what I want to do is I want to make a table for f of x and a table for f inverse of x and kind of see from that what's going on with this inverse function. How does this inverse function really work? So for our original function, let's plug in the values -2, -1, 0, 1, and 2. And so we're going to first just fill out this table just for f of x is equal to x cubed. So -2 cubed is going to be equal to -8. -1 cubed is -1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. So this is kind of a funny function in the sense that we do have a lot of numbers that are actually, the input matches the output. And that's just because of how the cubing function works, if you think about it. But most values are not going to have that, right? If you cube -2, it's going to be -8. If you cube +2, it will be +8. And same goes for lots of other numbers. So what I want to do is just make a table for what this inverse function is going to look like. So we're going to be putting x values and then inverse function values. So how does this work? Again, let's just maybe write down a couple of these a little more explicitly, and then we'll kind of continue to fill out this table. So for example, we know that f of -2 is equal to -8. And so what would that tell us about the inverse function? It would tell us that f inverse of -8 is equal to -2. And so that means that when we fill out this table, we want to put -8 as the input and -2 as the output. And so we can continue in the same way, and basically the input and outputs are just going to switch place. And so as I said, that isn't super interesting for some of these because they actually are just the same number, right? We end up with 0 and 0, 1 and 1. But again, here we see a difference, right? We see that when you plug in 8, you get 2 because of this kind of reversal that happens with the inverse function. So what would be the formula for this inverse function in general? And this is something by the way, we'll talk a lot more about in our next video, but I just wanted to kind of introduce this idea of the formula for an inverse function. So the original function was taking numbers and cubing it, right? We would do 2 cubed and get -2 cubed, get -8, -1 cubed, get -1, etc. So what is the inverse function doing if it's taking an input of -8 and getting an output of -2? Well, it's taking the cube root, right? From here, we can conclude that the inverse function is the cube root function. And so that's something, like I said, we're going to delve a lot more into this, but when you have a function defined by a formula, its inverse function is going to basically be the reversal of that formula. So if your original function is cubing, well, what's the opposite of cubing? It's taking the cube root. So one last thing I just wanted to quickly mention is that if you have a function that is not 1-to-1, you actually can kind of force it to be 1-to-1 in order to have an inverse function. So we're going to find a domain restriction to make the function f of x is equal to x minus 1 squared 1-to-1. So let's start by sketching the graph of x minus 1 squared once again. So we did this one earlier, and it was an example of one that was not 1-to-1, right? That's like why we even drew it. Sorry, I'm getting a little crooked on this. There we go. That's better. So basically what we want to figure out is how could we take this graph and kind of alter it so that it was actually 1-to-1. And so it's really not that complicated. All you actually do is kind of delete half of your graph. And so the typical thing that you'll do with quadratic functions, with functions that are parabolas, is that you'll take the right-hand side of the graph. And we'll talk a little bit more about why that is in a future video. But what we'd want to do here is we want to basically just kind of cross out this left half. And so what would our domain restriction be, or what would our new function look like with the domain restriction? We would say f of x is equal to x minus 1 squared, and then we would say x is greater than or equal to 1. And so that would be the function that starts here and just goes on up from there, and that does not include a left-hand side. Because now this function actually is one-to-one, right? It passes the horizontal line test. And so we'll come back to this example in the next video to see what the formula for its inverse function is. But I just wanted to show you that even if your function's not one-to-one to begin with, sometimes you can still come up with an inverse function. You just have to add this kind of domain restriction. All right, I will see you all in our next video.